Mr. Esmonding was like, oh look, it's our neighborhood sperm. Also to give us a visit.
Memorizing all the numbers of reactants and products of the Krebs cycle for aerobic respiration. It's like something
I remember learning that.
36 ATP are produced at this stage.
I remember studying that. I looked at the molecules and how the bonds happen. That was fun. But there was no memorization behind it, so it
At
was
least
just.
we already learned most.
It feels like a Friday, and I want it to be Friday. I just want to go home and sleep and study because I feel like I'm like behind.
Alright, let's get started. Your conversation was well recorded.
Oh,
Talking about sperms.
bio kids.
Alright, so we'll start the topic 4 review. I divided the chapters, and I think I could summarize into 3 parts. So we had the talk about the data, and the probability, and the random variable, and distribution. So hopefully we'll get through this relatively quickly compared to last time. Okay, so let's start with writing down the sections. So first we have the data. And then we have the probability, and we have the random variable, and then lastly we have the distribution. Right, so let's start from easy stuff about the data. So when we have the data, we either have a list of data. So one case is just list of let's say 1, 2, 5, 4, 4, 3, and da da da. So this is like a list of data. Another type of data that we'll have is the frequency table, where we have 1, 2, 3, 4, 5, and the frequency is 7, 10, 12, 9, and 6, for example. So this is the value and the frequency, like this. And then we could either have 2 values together. I think or 2 list or 2 variables of let's say x value and the y value, and then goes 1 and then 2.2 and then 3.2 and then 6, let's say 7 and then 14.7 and such. So these are some types of data that we have. For each of them, we can try to find how to analyze the data. So after we have these type of data sets, let's try to analyze it. We have either the center of the data, we also have the spread of the data, right? And we also have the correlation of the data. Let's start from the center of the data. What are some types of center of data? Well, we can start easy by saying the mean, the median, and also the mode, right? How do you find the mean? Well, we simply just add the values together and then we divide it by how many numbers there are. Median, we list them up and we order them from lowest to highest, and we select the middle value. And also we find the mode by finding what is the most common one. For either the list or frequency table, we can easily use our graphing calculator to find the mean and also the median. So what you can do is, if you have a calculator with you, you can press Stat and Edit, and you can, for example, type in the data set like this. Okay. Let's try to reset, and then let's enter some our new list. For example, we can go 1, 2, 3, 3, 4, 2, 1. Let's say, for example, like that, right? And then we can do stats again, and then calculate. So in this menu, stat calculate, we can calculate a lot of things that we're interested. The difference between the one variable stats and two variable stats is for one variable stats, we're dealing with one type of data. So obviously, if I go back to this type of data here, for the list or the frequency table, we're going to use the one variable stats, right? So let's try to use the one variable stats here. And then there's a menu where you can type in the list and also the frequency list. So obviously, if you just have list, then you're just going to type in the L1 and then you're going to calculate. If you have a frequency table, then we're going to enter the frequency on the L2, and then we can input that here, and then you can calculate it as well. So let's try to calculate and see what we get. For the simple data that I just put in, I see the mean turns out to be the x with a bar above it, so it's going to be 2.29. And then we can also, if you scroll down, you can find the mean, the minimum, the Q1, median, Q3, and max. So if you want to know the median, you can find it like this. Right? For the mode, we can just count it ourselves, or Q1 and Q3 we'll talk about in a second. Okay. One thing to note, to find the mean, sometimes there's a problem when you have the frequency table of grouped data. So let's show another case of that. So let's say we have another case of this time the value and the frequency. So let's say we have the 0 to 10 or 0 to 9, and then 10 to 19, and let's say 20 to 29, and let's just put one more, 32 to 39. So this is an example of a grouped discrete data. Group discrete data and group continuous data, kind of the same thing. But one thing to note is that this time we just have the range of values. So then if you have the frequency, let's use the same values, 7, 10, 12, 9, then we don't know for that range of 0 to 9, we don't know how many of those 7 things are either in 0 or 9, or whether they're spread apart. So we have to assume this special column called the mid value, the midpoint, however you want to call it. So you need to find the midpoint. For a group discrete data, where it goes like from 0 to 9, what is the middle point? Well, we can think about it. From 0 to 9, there are 10 points. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So then we have to find the middle point. So 0, 1, 2, 3, 4. So we can say the midpoint will be 4.5. Because the fifth point is 4, sixth point is 5. So the midpoint, the median, will be 4.5. So then it goes like 14.5. And then after you find the midpoint, then we can use this midpoint as my L1. And then I put the frequency L2, and then we do the calculation similarly. But this time, because we're estimating, the question will tell you not to calculate, it'll tell you to estimate the mean or something. Right? So that's one way to find the mean. We can also talk about the idea of the cumulative frequency, but I think we'll talk about it in a second. We'll add on to this later. Okay. So these are the 3 types of center of data. Now let's talk about the spread of the data. We can represent the spread of the data in multiple ways too, but first thing we can think about is the range. Range is it's not in the formal booklet, but it's just max minus min. And then we also have the interquartile range. In the formal booklet, you see it as Q3 minus Q1. Basically, the Q3 is, if you have your data as a percentile, then your smallest number will be the 0th percentile. The highest number that you have will be the 100th percentile. And your median, so this is your min, and this is your max, this is your percentile. Your 50th percentile is your median. Right? You list out the numbers, and the middle number is the median. Right? The 25th percentile and the 75th percentile are equivalently the Q1 and Q3. Okay, so basically you find the median of your data set, and then you find the median of the upper half, and that's your Q3. Then you find the median of the lower half is your Q1.
They ask us to find this without calculator.
It's not too difficult. You just find the median like 2 more times. It's quite annoying. So that's the meaning of Q3 and Q1. And as we've seen just now on our calculator, it shows you the Q1 and Q3, so you can use that. So for example, for this data set, I have the IQR, the interquartile range of 3 minus 1, 2. Also, we have the range of 4 minus 1 and 3. So these are some types of the spread of the data. One more example of the spread of the data is, of course, our favorite, standard deviation, which usually uses a notation, sigma. So do we have to know how to calculate the standard deviation with our formula? No. So we're not going to find the standard deviation manually, but it's helpful if you know the concept of it. The concept of the standard deviation is you find the average distance from the mean. So for each point, we find the distance from the mean, and then we square it to make it positive, and then we divide it by the n, the number of points, and then we do square root. This way, we can keep the standard deviation the same unit as the original data set. We also have the idea of the variance, which is, using the formula, it's achieved before we find the standard deviation, but the variance is, if you know the standard deviation, the variance is the sigma squared. You square the standard deviation and you get the variance.
What's the use for it?
What's the use for it? No idea. But sometimes in the formula, they give you the variance or they ask you to find the variance.
Square root it? Does that work?
Basically.
Well, the normal distribution, we just plug it in there
Yeah.
to express it.
On the calculator, we see it in the first menu of the one variable stats. So we have 2 types, but one thing we have to remember that in our IB curriculum, we're always going to stick with the population standard deviation, which is, we use the one that says sigma x on the calculator. Okay, the sigma x is the population standard deviation. The SX is the sample standard deviation that we don't consider in our curriculum. It's always going to be the sigma x. Okay. Before we move on to the correlation, let's talk about some methods of representing the data. So the representation of data. So we can represent the data in multiple methods as a frequency table, of course. We can also represent the data using a box and whisker diagram, or box and whisker plot. The box and whisker plot basically uses a diagram that looks like this, where you have 5 points here. This is your min, this is your Q1, this is your median, this is your Q3, and this is your max. So we call this a 5-number summary. You don't have to know the name of that. But box and whisker, we use these 5 points. Right? And of course, we can look at the size of the box, we can look at the range, we can look at the interquartile range and such. We can also represent it using a column graph. from the frequency table. So to use the column graph, we have the range and the frequency. And then we also have the cumulative frequency graph. Cumulative frequency histogram? I don't know, something like that. It's called graph. So what we mean by the cumulative frequency, by the way, the column graph has a shape like this, whereas the cumulative frequency will have a shape of something like this, right? So what do we mean by the cumulative frequency? Let's go back to the previous example. For cumulative frequency, we need to add another column. The cumulative frequency, let's call it FRE. What we mean by the cumulative frequency is every time we add a frequency, we're just going to add them. So from 7, the next we have 10, so we have 17. 7 plus 10 plus 12, 29, plus 9, 38, and such. Okay, we add them up. And then, every time we find the value, we're going to plot the point of how many there are. You use the range. So from the lowest point, so first, I'll start by plotting 0, 0. So at value 0, I have the frequency of 0. And then by value 9, I have a frequency of 7, right? So then we can draw it cumulatively, and then it kind of, you're estimating. So then from 0 to 9, there are 7 people, and 10 to 19 is 10 people, and such.
It's not a smooth graph, it's like choppy.
So if for discrete data, yes, it'll be choppy. For continuous data, it can be more smooth. What is a good use of this? So this is the value, and this is the cumulative. What is the value of this? We can add another axis on the right-hand side, and this can be called the percentile. So we have the percentile axis, the highest point being the 100%, and the lowest point being the 0%. And then we can easily find whichever percentile. Like for example, we can go, oh, what is the 80th percentile? Then we just go left and then down and such. Okay, so you can do that. So cumulative frequency graph is useful for the percentile. Okay. Right, so we talked about the representation. And then I think we need to talk about the correlation, right? We'll talk about everything else. Oh, the outlier. I forgot about the outlier. Sorry, my bad. I'm kind of jumping around. When we talk about the interquartile range, we have a spin-off case of talking about the outlier. The outlier, we have two boundaries. The lower boundary, which is Q1 minus 1.5 IQR. And the upper boundary, we have the Q3 plus 1.5 IQR. So if you have any points that are lower than the lower boundary and higher than the upper boundary, then we have to exclude that in our data. Or we can identify them as an outlier. Sorry about the jumping around. Any questions so far about the center of the data and the spread of the data?
Do we have to like consider outliers when we're looking at like problems in Excel?
I think the question will be more explicit on it and be like, hey, here's an outlier, or can you find the outlier, or like what we do with the box and whisker. By the way, for the box and whisker plot, if you have an outlier, we represent them as an asterisk. And then we don't include it as maximum. So after you find an outlier, you need to find a new maximum. Okay, if you have no other questions, let's talk about the correlation, the last part. So correlation is more, happens more so when you have like a table of two values side by side, right? So when you have the correlation, we can first find the value of R. which is you don't have to know, I think. I always forget. Pearson's product moment correlation coefficient. I only remember this because I looked at it like a couple minutes ago. You don't have to know how to find it, but we should know how to find it on the calculator. Okay. And then, okay, so let's talk about R value. So how do you find the R value? First thing we need to do is, let's talk about the linear regression and then we'll look at the calculator. And then the second part is the linear regression. So we either have the case of linear regression of y on x, and also we have the case of x on y. Long story short, y on x is the default. Right? If sometimes the question asks you specifically for the x and y, then you need to do some minor changes, but we'll talk about that. First thing we need to do on the calculator is that we need to set up a setting. So for what we want to do is you want to press second 0 to access the catalog. Basically, the catalog is a master list of all functions that exist in the calculator, and it's quite a long table. So let's press alpha D, so alpha x power of -1, to go to the D menu. Okay. And then if you scroll down, you see the diagnostic on. So you're going to turn this on. So press enter a couple of times, and then you see a screen like this, diagnostic on. Now let's try to find the correlation coefficient, and also the linear regression. So in the stats, I'm going to put in the points of the extremely short list of stuff. Let's put the two lists that you see on the top left here. So 1, 3.2, and 7. And just for fun, let's add in one more. Let's say 8.1, let's say. And then on the Y list, L2, I'm going to put 2.2, 6, and then 14.7, and then let's say 15.4. I don't know what I'm doing. So on the calculator, it looks like this. And then let's do stat, calculate, and then, okay, first of all, in the calculate menu, the two variable stats. So this one basically allows you to calculate the stats of each x and y separately. So you see there's a stat for the x. If you scroll down, we also see the stat for the y. And then they also show you some other information. So if you're interested in that, you can do that. Otherwise, we don't have to use this too many times. So let's focus on the linear regression ax plus b.
What is the 2R stats for again? Do we
If-
use it in our...
You don't really have to, but
What's diagnostic?
diagnostic on
Yeah.
is to turn on the Pearson correlation to appear. Two-word stats is useful if you ever have like multiple list of stats, or like if you have x and y, and then you want to look at the mean of the first one and the mean of the second one. On today's review, there was one question that you had x stat and the y stat, and then you have to find the mean of each.
Yeah.
Then you can just do two variable stats to do one, but you can also do the entire same thing by doing the one variable stats with L1 and then doing another one variable stat with L2. So there's not really a big point. Anyways, for the linear regression ax plus b, you can just see it as x list, y list, L1, L2, that's good. And then if you want here, store the regression equation, we can type in vars y vars function y1. What it does is whatever result that you get, you will save this result on y1. So you can immediately start graphing it afterwards.
Amazing.
And then let's calculate, and then, sorry, wait a second.
Second catalog.
Okay, there you go. Yay. So after turning on the diagnostic, I see the values of A and the B and also the R value. So we can say that we have the linear regression. Okay, let's talk about the R value first. So R value is, I have a 0.995. So what does that mean? The correlation coefficient tells you how well the two data sets are related to each other. If they show a, some kind of relationship, if like one grows and the other grows nicely, then we have a high value of R going up until 1. So if it's a positive relation, then we have a positive value. If they are a negative relation, which means that if one goes up and one goes down, we have a negative value. If it's closer to 1 or -1, the relation is strong. Right? And then we also have the values that are closer to 0 if the relation is relatively weaker. So in this case, R equals 0.995, we're extremely good. That the points are always very close to the middle, the mean, the regression line. So let's try to graph this. So we can try to graph this by first turning on the stat plot. So momentarily, let's just scroll down a bit in our notes. We have a fifth way of representing the data is the use of the scatter plot and also the linear regression or the line of best fit. Right? So let's try to use the scatter plot and the linear regression, which by the way will probably usually look like this, and then you have a linear regression like this, right? So how do you do that? On the calculator, you turn on stat, you go to stat plot, y, second y equals, and then you go to a screen like this, and then let's turn it on. So you press enter. That's kind of complicated, but let's press on. Okay. And then you go to y equals. If you followed this correctly, we already see y1 is equal to 1.96 blah 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 x plus 0.104, right? And then now you graph this. We already see a graph like this. We see the scatter plot and also the linear regression line, which definitely looks strong. But in order to capture all the stats that we want, let's go to zoom and then zoom stat, so zoom 9. Then the graph will automatically change the window to include all the data points. Of course, you can do this manually. So you see why this graph and why the R value is so strong, right? The graph looks good, that it's going through the middle point. 2 points are above the graph and 2 points are below the graph, so that's very fair, you could say. And also all the points are very close to the linear regression line, which is another evidence of saying that the R value is extremely close to 1. Any questions about the linear regression?
So I remember in the textbook there were being stuff like if R value is more than 0.86, it's a strong correlation. It's less than this.
Yeah.
So do we need to know those numbers?
I think that's unnecessary. And by the way, if you ever want to find the linear regression of x on y, what you would do, so here, x on y, what would you do? Is you go to stats, calculate, you do the same linear regression here. But then, this time, instead of typing L1 and L2, you can type in L2 and L1. Like this. Then, you will get the result. And it looks like this. This time, because we swapped x and y, you don't read it as y equals 0.504 x plus 0.005 or 450. This time you read it as x equals 0.504 y minus 0.00450. So then you can rearrange the y, rearrange to isolate y variable. Okay. And I think that's about it. We talked about the linear regression, Pearson's product model correlation, representation, outlier. Okay. Any questions about the data sets using calculator? All right, otherwise, let's move on to the probability. Okay. All right. Let's move on to the probability. So for probability, we first have to think about the difference between addition versus addition, is that right? Addition versus multiplication. So when do you ever add the probability? We can take a look at the formula booklet to think about it more easily. So you think about doing adding the probability when we're doing the combined events, right? So when you have the combined events, which means that we want to find A union B. A union B is another colloquial way to read that. Union, we read that as or, right? So union, it's kind of like, we incorporate all the things. So or is a bit like, you're either this or this, you're all invited, kind of thing, right? So we do that by doing the probability of A plus B minus the probability of A intersect B. A intersect B is, colloquially, we read it as and. So it's a bit more picky about that, A and B. Why are we doing this? Because on the Venn diagram, you can imagine A and B overlapping. And if you want to find the overall area that A or B possesses, then we have to do A plus B, but then when you do that, we double count the intersecting part. That's why we subtract it by probability of A intersect B. On the other hand, sometimes we have to multiply the events together when two events are happening together to find the A intersect B, right? A intersect B is probability of A and B. How do you do that? For independent events, we need to multiply the probability of A times the probability of B.
What's independent event and combined event?
So they're completely unrelated to each other, first of all. Combined events means just we have two events and we're trying to find either A or B. In that case, there's one other case, which we'll talk about as well, when we talk about the use of Venn diagram versus the tree diagram. So for the Venn diagram, it makes sense, right? We have A and B, and then we find the sum by doing the A plus B minus the intersecting parts. For the tree diagram, it looks like this, and then it looks like this. So then we find the probability of A and B happening to be like A and then B happening. So if it's like A here, A not here, B, B not, B and B not. Okay, so you multiply the events when you want to find the intersection, or you add the events when you want to find the union. Okay. And then there's third part about for each addition and multiplication, the Venn diagram, tree diagram, we're still always doing the same thing. And there are some exceptions, right? Sometimes we have the difference. Exceptions are when we have the mutually exclusive events versus the independent. Mutually exclusive, visually, it means that we have a Venn diagram, but then the A and B are completely not overlapping. So by the definition, although it does not say on the formula booklet, I think it's beneficial for you to understand it as probability of A intersect B is 0. That's the definition of what mutually exclusive means.
So two of them can't happen at the same time.
They cannot happen at the same time. So, if you assuming that, let's say we're like kindergarten kids, it can't rain and be shiny at the same time.
Yeah.
Although it happens sometimes, assuming that we're all kindergarten kids, it can't be shiny and rainy. What about the independent? Independent, visually, we can use a tree diagram to explain it. if you have the, let's say we use above similar thing. If the probability of B of the second, the column, let's say the probability of B happening is, let's say it's 1/3 and 2/3. If it's also 1/3 and 2/3, regardless of what A happened, whether A happened or A did not happen, if they're equal to each other, they're independent. Right? So we can write the definition as probability of B is the same thing as probability of B given A happened. And also the same as probability of B given A did not happen. Right? Basically, this equation, this definition is that I don't care whether A happened or not, B is still happening. The same probability. So that's the explanation of the independent events. When you have the dependent events, then the probability will change depending on it. So then this equation will not be true. One thing that we should be thinking about carefully is that mutually exclusive and the independent events are completely unrelated to each other. Right? They're totally unrelated concepts. They appear in the same box of the formal booklet, but they're totally unrelated. So you have to be careful that you don't mix these two up. I try to represent this. I try to represent this in a column. So addition, Venn diagram, mutually exclusive are kind of one thing. And multiplication, tree diagram, and the independent events are also kind of one thing. Okay.
But I don't understand in which case do we add the probabilities?
Venn diagram.
If you add the probability together, if you want to find the union. The union is either this or that happen, or both.
Okay.
Yeah. For example, if you want to find a probability that you get either A or B in a test, then you'll be adding the probability. But then if you want to find the probability of passing the test and the weather being shiny after the test, then you'll find the multiplication, because you're doing this and that.
Okay.
If you want to find this or that, then you have to do addition.
Okay.
What we kind of briefly talked about here is the existence of the conditional probability. Which is basically us saying that it's probability of, let's say B given A is probability of B intersect A divided by probability of A happening. So if given A happened, what is the probability of B? So we're assuming, at this point, that B and A are dependent of each other. So A happening will definitely affect the probability of B. So then it's going to be different from the probability of just B or probability of B given A not happening.
So this is the probability of B given A happened.
Yeah. B given A happened. So we read it as B given A. I wrote this in this order specifically because, alphabetically and in our tree diagram here, I wrote it as A happening first and then B happening. So it's a chronological order that A happened, so B is happening or not, right? So that makes sense, right? Except sometimes we have the Bayes theorem. I recently learned that it's Bayes with an apostrophe and no S after it. What is a Bayes theorem? Think of it shortly. It's a reverse order conditional probability. So basically, you're trying to find probably A given B happened. What does that mean? Well, A given B. Well, A already happened, And then we're saying, given B happened, what is the probability A? It's going backwards. So I think the key word here is the reverse. Sometimes in the question, when you're reading through the probability question, you'll encounter these like weird scenarios of going kind of counterintuitively backward in time. That's the sign that you should use the Bayes theorem when you're going backwards in time. Okay? So then we have the formula of using the Bayes theorem here. There are two cases. So if you ever want to find the probability of B given A, then basically you follow the steps of basically what you're doing. You're on the denominator side. You're finding the probability of A happening. Probability of A happening. Or if you have 3 or more cases, then we have multiple cases throughout, and then we add them all together. Okay. So that's why if you just want to stick with the conditional probability formula, that's also okay. If you're comfortable just finding the probability of the denominator side, the given that happening, you find that by doing addition of different probabilities, right? Anyways, I think that's about it for the probability.
A given B?
I noticed that I kind of wrote them in different order, but basically, conditional probability is when the order makes sense. Bayes theorem is when the order does not make sense.
But what
What
is
if
it?
they just stopped?
Yeah, and it doesn't matter too much. The formula is just formula, right? The B and A can always change. I think, in my opinion, this formula is kind of counterintuitive.
Should be A given B.
That's my opinion. And this conditional probability, B given A, should be B given A. That's my opinion.
Or
If I have a choice, I'll.
could it be, is it read as like A given B? Or
Yeah, it is.
or like
But
Okay,
it's
so
the same
we
as-
can forget the A and B. Okay, forget the A and B. If the order, the timeline makes sense, you use the regular conditional probability. If the timeline does not make sense, you use the Bayes theorem. For example, like if you want to find the weather of Friday, given that it was sunny on Thursday, it makes sense, right? So then you use the conditional probability. But if the question goes like, hey, what is the probability that the Thursday was sunny, like if Friday was raining? Then it doesn't make sense, right? It's a reverse order. That's when you use the Bayes. Yeah. Any questions about the conditional parts? Okay, let's move on to the next one. Let's talk about the random variable. Let's go my cheat sheet for a second. Okay, so random variable, we have two types of random variables. First, we have the discrete random variable, and then we also have the continuous random variable. Continuous. So what is a random variable? Random variable, like x or whatever value that we want to choose, is the probability of that value happening. Right? So both discrete and continuous random variable, or let's talk about discrete and continuous separately. So discrete random variable can be shown in some ways, such as the probability, the distribution table. Okay? So for example, it can be like probability that x is 1, 2, 3 is going to be probability that x is equal to x will be, let's say, 0.2, 0.5, 0.3. So this is a usual way to represent the discrete random variable. It means that probability that you get a 1 is 0.2. Probability that you get a 2 is 0.5. Probability that you get a 3 is 0.3. We can also have the probability distribution function. Probability. Let's just call it. I'll skip the probability distribution function. So for example, probability of x is equal to x is equal to, like, let's say x squared. For example, it's not really going to be like that. Let's call it like 1/4 x squared for like x from 0 to 5. Let's say, I don't know. It won't be right. Same thing for continuous later, but we should know that the sigma of probability distribution function is always going to be 1. Same thing for the continuous parts. Probability of all sum of all probability must be 1. That's a given fact. And then we can talk about the mean, the expected value. So I don't think it tells you in the formal booklet. Yeah, like I think it's quite easy to forget, but expected value, at least in the discrete random variable and the continuous random variable, expected value is the same thing as a mean, right? So how do you find the expected value or the mean of the discrete random variable? We simply sum the values. We multiply the value by the probability of that value appearing. Okay. So for the above example, expected value will be 1 times 0.2 plus 2 times 0.5 plus 3 times 0.3. So it's going to be 0.2, 1, 0.9, 2.1, something like that. Okay. We also have to find the variance and the standard deviation, which we can use the formula in the formal booklet. We can stick to the formula on the bottom side. The variance of a discrete random variable x is given by the sigma of, this time it's similar to the mu, but it's x minus mu. The mu is the mean, right? X minus the mean expected value squared times the probability of that happening. Okay. That's one way to do it.
What is the difference between mu and x with a line on top?
They're the same. X with a line on top is the mean. Mu is also mean.
I think mu is population mean, x with line on top is sample mean.
Really?
Or is
Shut
it
up, we know
naked
what mean.
stats?
We know.
Nerd.
I've never known.
Nerd.
That's, you're probably right.
In
You probably have a
Math
bit more statistical knowledge than me because I've never taken a statistics course.
In Math HL, population and sample they just make the same thing.
Makes sense. So anyways, this is how you find it. So you can kind of think of it as variance is the expected value of x minus mu squared. Also, it's the same thing. It depends on which formula you want to use. You can also do the sum of x squared times the probability, and then you do minus mu squared. So you have 2 cases. And also, if you want, you can do expected value of x squared minus expected value of x squared. So you have 2 different ways to solve the variance. And then, of course, to find the standard deviation, you simply find the square root of the variance. I think we can also do the discrete random variable using the calculator too, right? Let's try. Let's try to put this value. So what I'm going to do is go to stats once again. Try to put in this value, 1, 2, and 3, and then 0.2, 0.5, and 0.3, like this. And that's one, obviously. Basically, this is kind of like the frequency table, right? Except this time on the second column, instead of having frequency, we have the probability, which are basically the same thing. Sorry?
Yeah,
Does
sorry.
add to
Ready?
Yeah.
So once again, let's do the L2 for a frequency list, right? And then you calculate, and yes, I was right. So we know that the mean is 2.1, and then we see the standard deviation of 0.7. So we can assume that the variance will be 0.49. Is it?
Standard deviation is just the square root of
Wait,
variance.
why? The mean is 2.1. Why is the sigma x also 2.1? Like,
Because sigma x is when you add the values together, right?
yeah.
So it's,
how can you get like?
remember that mean and the expected value are the same thing in the discrete random variable.
Okay. So we got here with the frequency list.
Yep. So we looked at a case where we can use the calculator to find the expected value and also the variance and the standard deviation using the calculator and also using the formula. Any questions about the discrete random variable? Okay. All right, let's move on to the second part about the continuous random variable. Once again, we can use the probability distribution table. For example, you can go like x range from like 1 to 2, 2 to 3, 3 to 4, and then we have the probability of each happening. One thing we should know at this point, for continuous data, probability that x is equal to a specific value of x is always going to be 0, right? Because for using logic, that it's impossible to find someone who's exactly 170 centimeters. No one is exactly 170 centimeters. So instead, we try to find the probability that x is, less than 175 to 165, let's say. So you have to show it like this. Right? And also, we have the similar thing, the distribution function, probability density function. I think we see some examples in the probability density function. Right. Probability density function f of x, right? For some value, let's say 1 over 4x squared, we can do the similar thing. One thing we should also note, similarly, that instead of using sigma now, let's use the integral. From negative infinity to infinity, positive infinity, f of x dx, the sum will always be equal to 1. Similar logic. And then let's talk about the mode and median for a second here. So to find the mode of the continuous random variable, basically we have a probability density function, right? A function that looks like, I don't know, like this. The mode is basically you find the point at the highest. So that's going to be your mode. Right? For the median, you're trying to find the value of b such that the integral from negative infinity to point b of f of x with respect to x is 0.5. Right? So the median is the point at which the area from the lower half to that point is half the area. Which hopefully it makes sense if you think about it. And then let's also find the variance and the standard deviation, which is similar. We have the similar formula, except everything is swapped from sigma to the integral. So
Mu is mean, right?
mu is mean, yes. So once again, we have the expected value, which is the mean, which is this time sigma. Instead of sigma, we have the integral from negative infinity to infinity, x with
What is the max?
f of x dx.
That's what that is. That's
Yeah.
what's the density function. The y-axis is the point.
Okay,
The highest is the most probable.
I can already see the substitution somehow happening.
Yeah, I do.
Any questions about the mean? And the variance and standard deviation are calculated similarly.
Do they make us do this by hand?
I don't think so. But I don't think there's a way to input this
Yeah.
into the
I
calculator.
haven't seen a
Remember on,
question
the
about this at
calculator,
all.
3 people speak at the same time. Okay, you speak first.
I just remember on the calculator there's like PDF, like CDF, and I forget how to.
We'll talk about that later. Question?
Does it have to be a normal distribution?
No. We'll talk about the normal later. Yeah.
I don't think I saw any question like asking us to use these before. Are there any questions asking?
Well, they're in the curriculum, so you can assume that they will appear at any time when you expect them the least.
Yeah.
Okay. Lastly, we have the linear transformation. This part I actually have not seen, but sometimes, and it's not easy. It's not difficult, right? And good thing is that we don't have to memorize these. What is a linear transformation? We have it in the formula. The linear transformation of a single random variable, if you have expected value and you know the random variable x, but then if you, let's say, you multiply by an a, and then you add it by a constant, right? Then you have the new expected value. It's going to be a times expected value of the original x, and then plus b. And then also, if you have the variance of the new variable, then it's ax plus b, new variable ax plus b, then the new variance is a squared times the variance of the x. So you can assume it's not written here. Well, what is the standard deviation then? The standard deviation of random variable y, where y is ax plus b, it's going to be just a times the standard deviation of x, right? Because variance is square root of standard deviation is square root of the, what am I saying? Standard deviation is the square root of a variance, except this time we'll have to put the positive value. A will always be positive. The standard deviation can only be positive. Okay, it's not a difficult concept.
Is sigma?
Should I use sigma here? Okay, any questions about this random variable? I'm hearing a lot of murmurings, but let's move on. Step 4, last one, the distribution. Honestly, I think like distribution, now that I think about it, I think it's really fun. So if for distribution, we have 2 cases. One, we have the binomial distribution. And then we also have the normal distribution. And then later we'll talk about the standard normal. Standardized normal. So what is a binomial distribution? Basically, a binomial distribution is where we usually write it as x is distributed as binomially distributed with the parameters n and p, where n is number of trials and p is probability of success. Right? So for example, I think I had this question in a test last year. So let's say you have probability okay, assume that I wrote it right, of winning a match, let's say, is 70%, and 20 games are matched. 20 games are played. So then this is the case where we have the random variable x, where it's binomially distributed with n and 0.7. Right? So what do we do with this? Like this itself doesn't mean anything, right? So then at this point we can either use binom PDF. Binom PDF is when you want to find, hey, if I'm playing 20 games and the probability of winning is 0.7, what is the probability that I get 14 wins? Which is going to be something. So how do you find that on the calculator? You do second variable bars to go to distribution, and then you scroll down to find the binom PDF. So some calculators will show this, some calculators will not, but as I showed it, binom PDF has 3 inputs: trials, probability, and how many. So it's going to be 20, 0.7, and 14. So apparently, the probability that you have 14 wins out of 20 games is 0.192. So although it is the expected value, it's not that big, right? By the nature of the binom PDF is usually for the discrete random variable, because it's either how many times you do, it's either win or lose, or in such a scenario. You don't have to know the formula for the binomial distribution, but it's basically n choose r times probability of winning to the power of something, probability of losing to the power of something.
Is it 0.07, not 0.7? Because it said 7% win.
70%.
Oh, okay.
Yeah, I can't tell.
We can also have the binom CDF. Binom CDF stands for the cumulative. So if I type in the same thing, 0.7, 14, basically I'm trying to find the sum of 1 win plus 2 win plus 3 win plus ... all the way up until 0 win as well, until 14 wins.
Okay, so like the probability of having 14 or less successes.
Big. Yeah, 14 or less successes, yes.
Okay.
So if I try to find that, you type in the same thing, this time it's going to be 0.584. The probability that you get less than 14 successes, less than or equal to 14 success, will be 0.583.
Wait, probability that you get less than 14?
Less than or equal to 14. I think I should have written one more section, so I'm just going to add in one more part. Okay? So this is probability that x is equal to 14. And this one is probability that x is less than or equal to 14. Does this make sense? Let's talk about the expected value and the standard deviation. It's pretty simple. We're not going to talk about it too much. We already have the formula for them. So expected value which is the same thing as mean, of course, is just NP. We just multiply the number of trials and the probability. The variance is just going to be NP times 1 minus P. So the standard deviation will be square root of NP times 1 minus P. Okay. I think we can move on to the next part, the normal distribution. Normal distribution, we write it as x, let's use y this time. Y is normally distributed with the parameters. This time we're using the mu and the sigma. the sigma squared, where mu is obviously the mean, and the sigma is for the standard deviation. Okay. So how do I interpret this? Well, in order to understand the normal distribution, we have to understand first of all, normal is usually for the continuous random variable. We have to understand the 68, 95, and 99 rule. Right?
Oh yeah.
So what is the meaning of that? It means that if I have a normal distribution, we have a bell curve like this. And then from the mean and plus minus one standard deviation, minus one standard deviation, plus one standard deviation, this turns out to be 0.68 of the entire area under the curve, which entire area under the curve is 1, right? So it takes 68% of that curve. Or we could also say that there's a 68% chance that a value falls between one standard deviation away from the mean. And then if I go one more step, -2 standard deviation, and also +2 standard deviation, this is going to be 0.95. And also, lastly, -3 standard deviation, +3 standard deviation, this sums up to be 0.99. That's the meaning of the 68, 95, and 99 rule. So what do we use this for? So let's say we have the case where we have the mean is, let's say, 100, and the standard deviation, or sigma, is equal to 10, for example. Right? So then we write it as y is normal distributed as 110. Then we can ask a question of what is the probability that y is, let's say, less than or equal to, it doesn't matter at this point, less than or less than or equal to, because it's a continuous random variable, less than or equal to, let's say, 90. Right? So now how do you do this? Well, we're going to use the normal CDF. So you can go second variable of ours, distribution, normal CDF, which has a parameter like this. So you put in 4 numbers this time: lower, upper, and mu, and sigma. Okay? So lower, upper, mu, and sigma. So let's type in the information. The lower, it's going to be an extremely big number. So automatically it puts -1 times 10 to the power of 99, which is very small number, right? It doesn't matter whether you do it. You can just put it like -1, -10,000, -100,000, doesn't matter. Upper boundary will be 90 because I want it to be less than 90. And also I can put my mu will be 100 and the sigma is 10. So the parameter looks like this, and then you press enter, and the probability that you get less than 90 is apparently 0.159, 15.9%. And also we know that the area under the curve up until that. So basically, this less than 90 is from here to here. Right? Let's delete that. And of course, we can do this for greater than, then we just adjust the lower and then we fix the upper to be extremely big. Or we can also say, what if probability that your, we'll see an example here, right? Like 90, the y value is between 90 and 110. So then you can guess, what is the answer going to be? It's a direct fact, it will be 68%, right? Because the standard deviation is 10, and from the 100 of mean, it's 1 standard deviation away from each other. It'll be like 90, 110, 110, and we'll check if that's true.
exactly?
CDF.
No,
we
no,
have
right.
to
it's not
write
exactly.
using GDC, right, as a method.
Yeah,
When do we use normal PDF?
I've
When
never
it's a-
put that before.
When it's a normal distribution and you want an exact value, I guess.
Yeah.
It's not really that
It's just a
useful.
Y value.
That's
I guess
fine.
if you
It's
want,
just a Y value.
yeah.
I don't know. I get something. I think it gives you the f of x,
Yeah.
Oh, yeah.
but by itself, it's not going to have too much meaning to it because probability of that happening is 0. And also, we can try to reverse this method. Okay, what if, let's say, I want to find like the 75th percentile. Right? So what do you mean by 75th percentile? 75th percentile means that if I split this entire thing into four parts, and it's going to be like from the entire population, it's going to be probability that you get into the 75th percentile, right? So where is that value? That's what the question is asking. So then in that case, if you have the percentile, we need to use the inverse norm. It looks like this, inverse norm. Maybe before that I'll write that as this is a case of probability that y is less than something. Call this a is equal to 0.75. Okay, so let's do the inverse normal, which again is the distribution, but this time we use inverse norm. So let's type in the area to be 0.75 and then 110. So area like this, which turns out to be like 106.7 or 107 approximately. So if I ask you to, this is work backwards, yeah, probability that the y value is less than 107, the probability is 0.75. Okay, so this is when you don't know that boundary, right? But you still have to know your mean and the standard deviation.
If you're given like range between, like if you have to have lower and upper, how would you do that? You know what I mean?
Yeah, sure, let's do a question like that. For this one, let's say you want to find the probability. I mean, actually, there's too many answers to that.
Oh, because you can shift it every.
Yeah.
Yeah. Okay.
Yeah, so then
You need to
you're
give
given
it
at
one
least
value,
one.
yeah.
Yeah, maybe like lowest. Given that the lowest value is 25th percentile,
Yeah.
then find like 50%.
And you'll
then
still do 0.75, and then you'll find that value. won't you? It will give you the same value.
Yeah,
because
okay, okay. Hypothetically, if I'm making up the question, let's say given that it's greater than 80, what is like 75th percentile of the rest of it? Then what I would do is I'll find the area of less than 80,
Yeah.
and then I'll do 75 minus that,
Okay.
or 75 plus that actually,
Yeah.
plus that, and then do the inverse norm to find the upper bound.
Okay.
You just asked a very strange question.
Okay.
You can ignore it.
So for the binomial binom CDF, it always gives less than or equal to, right?
Yeah, yeah.
For this one,
Inverse norm.
yeah, for the inverse norm, it's like
From 0.
0 to that point.
Yeah.
Okay.
From the negative
Yeah,
infinity
yeah.
to that point.
Okay, that's fine.
Okay. Right. Any questions about the normal distribution? We'll continue on with the last part, the standardized normal variable. So what do I mean by the standardized normal? As you can see in the formula, we just simply it's kind of a zone. I think of it as a zone. So you have the variable x, and then you enter the zone by doing minus mu divided by sigma. What is the meaning of this, however? what it does is we take whatever value that you have, whatever data set you have, whatever distribution that you have. If you do minus mu divided by sigma, it always turns out to be the new z, the standardized normal distribution. I think we use like z, right? Let's go back to x this time. X is standardized normal. Is it how you write it?
I think so.
This time the mean is always 0, and the standard deviation is always 1. Quite simply, right? You put everything into the middle, and then whatever standard deviation you have, it's 1 now. So that's what it means by standardized. We all have the mean of 0, and the standard deviation is always 1.
Yeah, that makes sense.
When do we use it? I remember we had a question last year.
Yeah, so when do we use this for? What do I use this for? This is useful. I think this is where the review session comes in handy, right?
When you don't know the
Standardized normal is
standard
useful
deviation.
when you don't know mu or sigma or both.
How'd you get Z? What was that again?
Well, systems of equations. Right?
Yes, we use systems of equations. Or if you just don't know one of them, then we can just use
Cases.
without the systems of equations.
Isn't it?
Okay.
What is it?
So then, knowing that the standardized normal variable always have a mean of mu and sigma, then if you have, let's say, a data set is given to you, but you don't know the mean, and the question asks you to find the mean, right? Then we first switch everything into the standardized normal variable
How?
with just minus mu and then whatever sigma you have, right? But then, so ultimately, it's going to give you a hint. For example, it's going to give you a hint such as probability that x value is less than 80 is 0.7 or something. That's one hint. Then with one hint, you have one equation. And then after you're doing the standardized normal, we have another equation, but this time you don't know the mu. So now you solve for the mu, so you solve for the mu.
So wait.
Wait, what?
So when it says like probability of this value being that you calculate how many sig figs it's away from, or is that
How many standard deviations? you have.
standard? It's not sig figs. It's standard deviations away from.
Yeah.
And then you calculate for the mean. Or
What's Z again? Like, what is it?
Should you do an example?
Yeah.
Okay. I need to think
is
about.
Z the same for like all cases, or is it different? It should be different.
Yeah, it has to be.
We just call it z value. The meaning of the z value.
Distributions.
Okay, let's talk about the meaning of the z value
Don't
before.
worry about it.
Z value. How many
Oh yeah. that was-
SD away from the mean a point is. You have a point, and z value is how many standard deviations away from the mean. Let's do an example. Let's say we have the probability that x is less than 70 is equal to. Should I make the numbers a bit lower? Actually, it's fine. Is 0.8, let's say. Right? And we also know that, should I not know the sigma or mu? Let's say we don't know the mean. For both, we need one more hint. So it's a bit more complicated. And the mu is, what should the mu be? So it makes sense. Oh, let's find the sigma. Sigma is 10, let's say, right? So then, what can we do? We know that z is x minus mu divided by sigma, right?
Yeah.
So let's find the new z for that 70 value. What is that 70? What does that 70 mean, right? So z is going to be 70 minus mu, find mu, divided by sigma, which is 10, right? So we transform that 70 using the standardized normal variable formula. So then this time, we have the probability that z is less than 70 minus mu divided by 10 is equal to 0.8. at this point, we know that Z is a, I think we say normal, right? We don't say Z. Someone lied to me. I think it's like
The
this.
Niels can't
Me.
We hate you, Kenta.
Okay, right. So then at this point, what do? We use a normal, inverse normal. So we do inverse normal of, what do? It's 0.8 and area is 0.8 and the mu is 0 and the sigma is 1. So what is that? I'm using the calculator.
We need
Diffusion,
4.
inverse norm, 0.8, 0 and 1. So 0.84842.
What does this value mean?
So it means that the 70 minus mu over 10 is 0.842 standard deviations away from the mean, or that's the value of Z. Right. So then we simply solve the equation. 70 minus mu divided by 10 is now 0.842. Right. So then mu, it's going to be times 10 and
7
minus that.
61.6.
61.6. So we know that the mean is 61.6. I can repeat the process in other case to find the sigma, the standard deviation. Or if I know one more hint, then even if I don't know both mu and sigma, then we use systems of equations to solve for both.
Is that it?
Yeah, that concludes everything. Okay.
I need to review this topic even more than this door.
All right, any questions?
No further questions.
No,
That
sorry,
went-
I like my attention span is gone.
That happens.
You had
That went a lot longer than expected, but thanks for staying here.